In this video, we're going to be discussing how to calculate changes in enthalpy and how to apply them to an energy balance. Now, the energy balance for an open system is given by the change in enthalpy is equal to the total heat into the system minus the total amount of work extracted from it. And if we recall, the delta H is written as the summation of all of the different mass flow rates times by their respective material properties out of the system minus the summation of all of the individual species and their respective enthalpies coming into the system. So the general form of the open system energy balance is relatively straightforward. The difficult part is how do we calculate the H hats. And H hat is going to be a particular material property and is going to have units of joules per kilogram, but we could also do all these expressions in terms of joules per mole as well. The connection here between how we write it as m dot H hat allows us to combine the energy and material balances in one continuous system in order to better solve different types of problems. It is actually not possible to absolutely calculate U and H, and as such we use reference states. To illustrate this point, if we consider a single, molecule, we'll say, or a single atom here, we'll say it's, hydrogen, we'll have a little electron that wiggles around it. The electron energy states are quantized, and we can really only solve very simplified systems like this. If we were to consider a more complex system, even as simple as a single, hydrogen-hydrogen bond, we have the bond vibrations are quantized. We have different molecular velocities. And let's say we were able to accurately and completely calculate all of this here. Remember that 1 mole corresponds to 6.022 times 10 to the 23 molecules. So you can see that trying to add up all of these different energy effects, and each of these do contribute to the delta H, right? So this will have some sort of a H associated with it, this will have an H associated with it, this will have an H. Trying to add up all of these things together to form a perfect and accurate model is something that's not really physically all that possible. However, what we can do is we can define a reference state. So in other words, put it, H cannot be defined absolutely. So instead, we'll take all of this and use relative changes. The good thing is that all processes that we care about depend on relative changes. And the good news is that regardless of reference state, all relative changes are the same. For example, if we were to look at a steam table, and the steam tables generally report U, H, specific volume, and all these different things as a function of temperature, maybe here, and then they'll have another table at, this could be at P1, you could have another table here at P2, and again, you'll have temperature going down, U hat, H hat, PV hat. Each of these boxes will be values that we can look up at a particular temperature and pressure. But you'll notice that at one of these cells here, you'll have U hat is equal to 0, and this will be the reference state. So when looking at a particular table, the delta U or delta H from some particular table will be the same as delta U or delta H from a different table. But one thing to keep in mind is never mix two different tables. One really important characteristic of delta H and delta U is that they are state properties. And what this means is that they are path independent. So one really easy way to think about this, let's say we were counting to 7, we could count up to 7 going from smaller numbers, 5, 6, 7, and we could count down to 7, 9, 8, 7. And the value or the meaning of 7 stays the same regardless of how you get to it. Now work, in contrast, is not path independent. It varies whether or not you try and move a boulder by kicking it or slowly moving it or pulling it with a pulley, right? So it matters how you actually go about doing work on a process. So if we're trying to calculate the delta H, the change in enthalpy from, let's say, solid ice to steam, we can break this process up into a number of different steps. So if we have a process here, we'll say, as we increase the temperature, we are starting down in the bottom right here with ice. In fact, maybe I should use blue for that. There's a couple steps that go about in the process. So first, if we have, in this case here, we'll call this H of ice, we want to find out how much energy does it take to heat up some ice at a particular, T1 and P1 all the way over here to steam. And steams will be hot, so we'll put it over here. Steam, which will have H of steam at some T2, and we'll keep the pressure constant for this calculation. Now in this circumstance here, if we wanted to try and go straight across here, it really doesn't allow us to go across physical lines. So what we'll do is we'll break this up into a number of different steps. The first is we will heat the ice to the melting point. And this requires what we'll call delta H1, a certain amount of energy to heat ice from whatever arbitrary temperature it is to the freezing point, and we'll say this is 0 degrees C if we're working at 1 atmosphere. Then we have another delta H contribution for melting the ice. We'll call this delta H melt. Then we'll have to heat the process again until we reach the boiling point. We'll have 100 degrees C. We'll call this delta H2. Then we have to vaporize the system, delta H of vaporization. And the last thing is we'll have to heat it up to the final temperature, delta H3. Now the total energy that it would take to heat up a certain quantity of ice at its initial temperature all the way to whatever the arbitrary temperature of the steam is would be just adding all these together. Delta H is equal to delta H1 plus delta H of melt plus delta H2 plus delta H of vaporization plus delta H3. And this is a really very useful technique that we can use to break up a large problem into smaller and easier to calculate steps. And this is only possible because delta H, or H, is a state property. The next important thing to cover is how to calculate these delta H values. And the same technique is applied to delta U as well, but we'll focus mostly on delta H, which is more commonly used in open system energy balances. The internal energy, in this case the specific internal energy, which would be joules per kilogram, for our purposes is going to be equal to a function of temperature only. H, again, specific enthalpy, is technically a function of T and P. However, if we look at it for an ideal gas, it actually becomes only a function of temperature in the first place. Enthalpy is defined as the internal energy plus the PV work that is associated with it. However, for an ideal gas, and this is what we are predominantly going to be using, PV is equal to RT. So if we perform the substitution, this is equal to U hat plus RT, and as we can see here, there is no pressure dependency. And that's because for an ideal gas, as the pressure goes up, the specific volume goes down, and that equals to RT. So if we're holding the temperature constant, we can see that the enthalpy is no longer a function of the pressure. And this here, we'll call this for after we talk about pressure changes, we'll move on to temperature changes. For a non-ideal gas, we can say that PV is equal to ZRT, and if we recall, this is the compressibility factor. So in this case, as the pressure goes up, the specific volume doesn't necessarily go down as a one-to-one, and if this is the case, H is function of T and P. However, what we're going to be focusing on is this case here. And so we won't worry ourselves too much about the non-ideal behavior. Now the next important step is to calculate delta H and delta U with changes in temperature, because as we discussed earlier, just the previous slide, there really is no pressure dependency for an ideal material with temperature and pressure. So next we'll talk about delta H and delta U. Two things are very useful for calculating delta H and delta U, and those are the specific heat, C sub V, which is defined as the change in internal energy as a function of temperature while holding the volume constant, and C sub P, which is defined as dH dt at constant P. So with knowledge of the specific heats, we are able to calculate changes in the enthalpy. So if we look at this graphically, if we are changing the temperature, and we'll start off with T1 and T2, the difference here would be delta T. And on this axis we will plot U hat, joules per kilogram. And we're going to be going from some U hat 1 to U hat 2. The specific heat is the slope of du dt. So if we were to plot this out, we could have some sort of an arbitrary curved surface. If we approximate the specific heat as constant. So if we say CV is approximately constant, effectively what we're doing then is we're saying that, no, actually let's draw U1 is here, so forget about that. We are at some initial condition here, and again, let's redraw this one here. And then we're going up to some condition 2. So this would be number 1, and this would be number 2. If we were to connect this with a straight line, that would be assuming that C sub V is equal to constant, in which case we would have delta U is equal to C sub V delta T. The C sub V would be the slope. But in actuality, delta U is equal to the integral from temperature 1 to temperature 2 of C sub V dt. And this is the more appropriate form that we would use, and the same formula would be for delta H, but the difference would be that we would have C sub P. In order to apply these equations, in this case we'll just do C sub P delta H is equal to integral from T1 to T2 C sub P dt. Thankfully, the specific heat is tabulated for many compounds, and the form that is most commonly seen is that C sub P is equal to a polynomial fit of A plus BT plus CT squared plus DT cubed. Another common form is that C sub P is equal to A plus BT plus CT to the minus 2. So what these give us here is the specific heat as a function of temperature. So then if we integrate them, we can calculate our delta H as a result of temperature. These are two common forms, but they may or may not be the only forms that you may come across. These are empirical fits. So the coefficients A, B, and C or D, they don't really have any specific meaning other than they fit the actual experimental data well. So always check the range. And that would be, you'll have a minimum temperature where it's available and a maximum temperature. And these are the temperature ranges that the fit is going to be accurate over. So if we were to actually use these equations to calculate delta H again is equal to the integral from T1 to T2 C sub P dt. If we substitute in the expressions from earlier, we can write that delta H is equal to the integral here, T1 to T2 of A plus BT plus CT squared plus DT cubed dt. This polynomial expression is straightforward to integrate, and we can develop an expression for the delta H. Substituting in the T1 and T2, we can come up with our expression for delta H as a function of changes in temperature. And this is an equation that will be very commonly used when we don't assume that the specific heat is equal to a constant value. Now we can get delta U by just modifying it slightly. A for delta H. Oh, sorry. We'll say that A for delta U, and that is this A coefficient here, is equal to A for delta H, which is in the tables, minus R, and this is for an ideal gas. And this is because C sub V is equal to C sub P minus R. So that's the only modification that needs to change when going from delta U to delta H in the calculations. And in order to describe where this equation comes from, we'll do a really quick derivation. We can write delta H is equal to delta U plus delta PV. If we substitute in the specific heats for delta H and delta U, we can come up with C sub P delta T is equal to C sub V delta T plus delta PV. Now if we take the ideal gas law where PV is equal to RT, we can substitute this in as well, so delta PV would be R delta T. C sub P delta T is equal to C sub V delta T plus R delta T. And from this we can easily see that C sub P is equal to CV plus R, or rearranging it, we have C sub V is equal to C sub P minus R. And that's how we can relate between delta H and delta U. So to summarize what we've talked about in this video, the initial starting point was to try and apply the open system material balance, which was delta H is equal to Q minus W. But inside of this term, we needed to have a series of specific enthalpies for each different process, each different chemical, each different stream. And now we have a strategy in order to calculate each of these material properties so that we can apply the open system energy balance. And ultimately what we're going to be interested in is how much heat does it take to run the process, or how much work are we going to get out of it. And that's all for this video.